Now the last part of this lecture is again on computation of integral, so we keep on doing some important substitutions, and the next example is the following. We have the integral between 0 and 1, you have to compute the integral between 0 and 1 of this 1 minus x squared dx. Okay, this is a strange kind of integral in the sense that this is not of the type here, integration by part, or it is hidden, this structure is very hidden. So this is an example of another category of integrals, the integrals that you have to compute by using some sort of smart replacement. Okay, there are many, there is a huge literature on smart replacement. We will treat some of them, otherwise it is not such a clever study to study by heart of the nice and smart replacement. However, this is quite important because it is widely used and you have to know it. And here, quite surprisingly, what you have to do is this: x is equal sine of t. And so this implies that dx is cosine of t dt. Notice that this is made in the reverse mode. So the new variable here enters inside a function. It is not t is equal some function of x. It is made on the contrary. Okay? So you immediately have here the replacement for dx. It is possible to act like that. It is convenient to decide an interval for t, and here since t goes from 0 to 1, since x goes from 0 to 1, here you can choose t to belong to 0 pi over 2. Okay? Since the sign is periodic, you would also use some other interval, but this is the easiest one, so this is what we suggest. And so this is indeed the integral between 0 and pi over 2 of 1 minus sine squared of t cosine of t dt. And this is the integral between 0 and pi over 2 of the absolute value of cosine of t dt, and this is equal of the integral between 0 and pi over 2 of cosine t to the square. Why? Because here the absolute value of this is equal to cosine of t, since t is in 0 pi over 2, and here in this interval the cosine is non-negative. This is cosine of t of dt. And this is what we already computed in the previous example with cosine squared, and we know that this is p over 4. So it is not Italian, it is English, so I say compare with the previous example. And so try to compute. You cannot solve integrals, you can solve problems, solve exercise, but compute integrals. So this is the integral between, start with the indefinite integral. So compute this indefinite integral, square root of 1 plus x squared. This is another example. And you have to find a smart replacement. This is not easy. Change of variable. replacement in the sense of change of variable. And another example is the following. Here you have the integral of the ratio between the polynomial p of sine of x, cosine of x, divided by q. These are polynomial in the variable sine and cosine. Q, sine of x, cosine of x in the x. And here the most automatic algorithmic way to do that is to write here the usual so-called, I don't know why, but they are called parametric formulas that says that sine of x is equal to 2 times tangent of x over 2 divided by 1 plus tangent squared of x over 2, and cosine of x is 1 minus tangent square x over 2 and 1 plus tangent square x over 2. Okay? You have in mind this formula. What is the advantage is that everything here is written by introducing this tangent of x over 2. It appears everywhere, no other trigonometric function appears there, and there are no square roots. Square roots are always a bit annoying because you have to decide whether the radicand is positive or negative and so on and so on. These are much simpler, so more algorithmic, more automatic. You don't have to reason too much. And so you can consider the substitution, the change of variable, t equal to the tangent of x over 2, which means that x is equal to 2 times arctangent of t, so that dx is 2 times 1 plus t squared dt. Okay? And what happens is that this becomes a polynomial. This becomes a polynomial. And so the integral is therefore turned into the following integral. The integral of p of what? Of 2t divided by 1 plus t squared, 1 minus t squared divided by 1 plus t squared, and here q. Here you have 2t divided 1 plus t squared, 1 minus t squared, 1 plus t squared, and instead of dx you write 2 divided by 1 plus t squared dt. Okay? Okay, this formula you don't have to remember it, but it is better to focus on some exercise, and so a concrete example, and a concrete example of this is whatever you want, so write down here. Sine of x minus cosine of x divided by sine of x plus cos squared of x dx, and then do the replacement we wrote before. So instead of sine of x, you write 2t divided 1 plus t squared, and instead of cosine of x, here you have minus 1 minus t squared divided by 1 plus t squared, and here 2t divided by 1 plus t squared plus 1 minus t squared divided 1 plus t squared to the square, and here instead of dx 2 divided by 1 plus t t squared dt. Okay, this is quite horrible. It seems to be really horrible, but something can be indeed a bit simplified by noting that here you have 1 plus t squared here and here, so you can cancel with this. And so go on, and here you can extract the factor 2, which is common to everything here. So, and here a denominator, you have t squared plus 2t minus 1, because t squared has a positive sign here, so plus 2t minus 1, add the numerator, and then here you have to consider that there is a denominator, there is a common denominator, 1 plus t squared to the square, so here 1 plus t squared to the squared, and here you have 2t times 1 plus t squared plus 1 minus t squared to the square. Indeed, it is still horrible, but not so horrible like before. And so you do some computation here and there, and then you find a lot of this is let me write it. This is 2 times. Let me write it in the following way, or we can do it. I'm not completely sure. Okay, let us do it. Why not? Okay, here you have 2 times t squared plus 2t minus 1, and here t fourth plus 2t squared plus 1, and here 2t plus 2t cubed plus 1 plus t fourth minus 2t squared in dt. So here you have 2 times, and here, okay, t6 plus 2t5 minus t4 plus 2t4 plus 4t3 plus 2t minus t4 minus 2t squared minus 1. Extremely horrible. And here a denominator, just order the terms, t4 plus 2t3 minus 2t squared plus 2t plus 1 minus 2t squared plus 2t plus 1, and this is all dt. I hope this is correct, just check it. And here, okay, 2 times, and here we have t6 plus 2t5, and here there is a minus t4 plus 2t4, so minus t4 plus 2t4 minus t4, very good, and plus 4t3 minus 2t squared plus 2t minus 1, and here And here we have here denominator t4 plus 2t3 minus 2t squared plus 2t plus 1 dt. And so we go on, and a good way is to try to end up with a numerator which has a lower degree than the denominator. So basically to divide these two polynomials. There are many ways to do that. Probably the laziest one is just to try to consider the two terms of higher degree here and here. The ratio is t squared. And here, so right here above this polynomial here times t squared, and see what happens. So here you can write t6 plus 2t5 minus 2t4 plus 2t3 plus t squared, which is this polynomial here times t squared. Okay? Of course, it is horrible, I know, because now we have to rewrite here the same polynomial that we had before. For instance, here we have minus 2t4, and so we don't have t4, so here we have to write plus 2t4. So here we have 4t3, here just 2t3, so write plus 2t3. And here plus t squared, here we have minus 2t squared, so minus 3t squared, and then plus 2t minus 1. And so we have the same polynomial, and here t fourth plus 2t cubed minus 2t squared plus 2t plus 1. And notice that this part here is exactly this, multiplied by t squared. So we write it like 2 times t squared plus what? Plus the remainder here, so 2t4 plus 2t3 minus 3t2 plus 2t minus 1 divided by t4 plus 2t3 minus 2t squared plus 2t plus 1 in dt. So now again we do the same with this. This is 2 times t squared plus what? So here the first term here is half of this first term here. So rewrite this numerator by starting by twice the denominator. So t squared plus 2t4 plus 4t cubed minus 4t squared plus 4t plus 2. So here we have the double of the denominator, and now we have to adjust. Here we have 43, here only 2, so here plus 2 t3. Here we have minus 4 t squared, here is minus 3, so plus t squared. So here we have 4t, here plus 2, so minus 2t. And here we have plus 2, here minus 1, so minus 3. We are almost at the end. And here we have t fourth plus 2 t3 minus 2t squared plus 2t plus 1 dt. So here we have 2, here t squared plus 2, so we used all this here, and here plus, plus, and here you have 2t cubed plus t squared minus 2t minus 3 divided by t4 plus 2t3 minus 2t squared plus 2t plus 1 dt. Now we know very well how to integrate the first two terms. So we have 2t squared, that is t cubed 2 over 3 plus, 4t. plus the integral of 2t cubed plus t squared minus 2t minus 3, and here t4 plus 2t3 minus 2t squared plus 2t plus 1 dt. And this seems to be really awful, lousy, but this is a rational function. You can always integrate it exactly, so bring your computation up to the end. We will see how to do it. The message is that a rational trigonometric function can always be integrated, but the integration can be lousy. Okay? And so let us go to another example, and another example is the following, that has to do with these functions, which are rational functions. Let us look for the set of primitives to the indefinite integral of this function, 1 over x times 1 minus x. And here the trick is to do the following decomposition. 1 over x times 1 minus x is equal to 1 over x plus 1 over 1 minus x. Every rational function admits a decomposition like that, where here you can have a first or at most a second degree polynomial. We will see it, okay? And this is what we do here. And now it is easy to integrate this function, because then the integral of 1 over x times 1 minus x is the integral of 1 over x plus the integral of 1 over 1 minus x. And so here be careful, because this is log not of x but of absolute value of x. And here again you have log of 1 minus x, but since there is a minus here, you have minus, and here there is c. So at the end you have log of the absolute value of x divided by 1 minus x plus c. And the message do not forget about the absolute value. But for me it is a serious mistake. Okay? But why do I say that? Okay. This is a remark I did during the last question time, and I want to stress it again. And and the remark is the following: is that the log of absolute value of x is equal to log x prime for x larger than 0, log minus x prime for x less than 0. So this is equal to 1 over x and 1 over minus x, but then we have to multiply by minus 1 because composition of function. So it is again 1 over x, also for x less than 0. So as a consequence, we have that the integral of 1 over x is not the logarithm of x, but it is the logarithm of the absolute value of x. Okay? Think of it, understand it, and never forget about it. It is really a serious mistake if you forget that. Okay? And so, okay, this is all for this lecture. In the next lecture, we will treat the method, the very powerful method of integration by parts.